Welcome to Hot Chips 18. Session 8, Communications.
Our first speaker is Yuri Cummings from Fulcrum Microsystems. Yuri is one of the co-founders of Fulcrum, a company that came out of work at Caltech. And even while Yuri was busy at Fulcrum making Fulcrum work, he actually finished his PhD at Caltech. We're proud of him for that. We call him the CTO, but he does lots of very high-level functions for Fulcrum, and he's here to talk about FocalPoint, the latest product from Fulcrum Microsystems. Yuri?
Okay. Huh. Well, good afternoon. I'm going to talk about FocalPoint, which is a low-latency, high-bandwidth Ethernet switch chip. But before I dive into that presentation, let me give you a very brief background on Fulcrum. We are a startup company with a little over 50 people. We've been at it since 2000. We were based, we started up to commercialize technology that we had developed in high-performance switching or high-performance circuit design at Caltech in the 90s, self-time logic and that sort of thing. And we've given presentations in the past at Hot Chips. So hopefully some of you have experienced those presentations. We now have two products shipping in the marketplace today. Our first product, PivotPoint, which I won't talk really much about at all, but just to say that we gave our first public presentation on PivotPoint here at Hot Chips in 04. At that time, we were just about to tape out the device. It's a switch which switches the SPI4 interface and is used in networking systems. And it has now been in the market for a couple years. It's in production. It's sort of quietly accumulated about 20 design wins, and we're very happy with that experience. But today I'm going to talk about FocalPoint, which is even a much more exciting device, and we think something which will change the way the data center is constructed, the networking in the data center. We are backed by 5 top-tier investors, and it's been a pleasure to work with such sound investors, as they've given us lots of advice and financial support through the very challenging times of 2000 to 2006. And so we're very happy at Fulcrum now. We think things are in a great state and looking forward to the years ahead. So that's the company background, who we are and where we came from. Let me now talk about FocalPoint. FocalPoint is the world's most powerful Ethernet switch chip. It has 24 ports of 10 gigabit Ethernet, all integrated onto a single chip, including the SerDes, the frame memory, the MAC table, everything except for essentially a commodity off-board embedded processor is integrated on a single die. In addition to having that density, it also has the lowest latency of any Ethernet device with 200 nanoseconds of in-to-out latency, or fall-through latency, which is as low as any common fabric in the data center and much lower than any Ethernet device ever introduced. It's low power, which is important, but in particular what we did in the design was we designed it with systems in mind. And we're looking at scaling up to thousands of ports of non-blocking switching infrastructure with a single building block. And I'll get into how we do that later as we go. And here's our reference design. And you can see that the switch chip is there in the middle with a small off-chip microprocessor. But really, there's nothing else on the board. So it really is a fully integrated switch chip. This is a 24-port rack switch, and there's 24 CX4 ports behind on the front panel, which aren't shown. So today for the agenda, I'd like to talk about the requirements in the data center, and then dive into the details, the architecture, and the feature of the FocalPoint chip, and then talk about applications which this chip makes possible. So one thing which is always very good to ask yourself before you build a chip is what problem are you trying to solve? And when we look at the data center today, we see that there are disparate technologies used to build up to 3 different types of networks. There's a cluster interconnect network, which is really optimized to be low latency and high bandwidth. And in the past, that's been proprietary solutions such as MirrorNet, and what I would call semi-proprietary solutions such as InfiniBand, or solutions without a very large ecosystem. There's also the storage area network, or SANs, which the storage guys tend to call the data network. And today, those are largely fiber channel solutions. In the SANs, low latency and port density are important, but also it's very important to have robust delivery. And so they're very careful about controlling those networks and guaranteeing the delivery. And then lastly, the comms network, or the front-end network, which everyone will agree, hands down, Ethernet is the uncontested winner in the comms network. And what really makes Ethernet valuable there is its plug-and-play capabilities and its interoperability and its very low-cost basis. Today, those the comms networks are port speeds of 10 to 100 to 1,000 megabits, and we certainly hope that they go to 10 gigabits in the future. So in our view, Ethernet has the virtues that would be ideal for all 3 of these networks in terms of features. Lots of people have added layer 3 through 7 features, but it's lacked performance. It's lacked low latency. And so our take has been to add low latency and port density to Ethernet. So in our view, the cost of communication really is the latency between communicating devices. So breaking latency down for a little bit, it seems that there are 3 constituent parts of latency. There's the store and forward latency, which is somewhat of a misnomer, but that's the last bit in to first bit out, or it's the time that the switch adds to the latency. So just as a great sushi chef is, the figure of merit for him is how few times he touches a fish before it gets to your plate. So for a switch, a figure of merit is how little latency the switch adds to the packet. Typically in Ethernet, we see between 2 and 5 microseconds of store and forward latency for most systems at the 10 gigabit level. The FocalPoint device is 150 nanoseconds of store and forward latency. Again, that's last bit in to first bit out. The other part of latency is packet serialization time. In a store and forward switch, and here we mean a switch which stores the entire packet into memory before it begins to switch it, at the 10 gigabit Ethernet level, that's 0.8 nanoseconds per byte times the packet length. And for gigabit Ethernet, it's 8 nanoseconds per byte times the packet length. For a cut-through switch, the packet serialization time is independent of packet length. And in the case of the FocalPoint device, there's a 64-byte segment which is stored in each switch, and that adds 50 nanoseconds. So the overall fall-through latency is 150 plus 50 equals 200 nanoseconds. There's a third component of latency, which is the scheduling latency. And by this, what we mean is when you want to send the packet out, if there happens to already be a packet on the line, you have to wait until at least that packet is done, the transmission of that packet is finished before you can go. Now, this we call the scheduling latency. Now, there's been a lot of switching vendors who have used the fact that scheduling latency exists to argue that you shouldn't make switches cut through because there are collisions and therefore you store and forward packets anyways. In fact, if you think about it, the scheduling latency applies to cut through switches and store and forward switches identically. It's just a question of when you finally decided you can start switching the packet, is there or is there not a packet on the line? And this is an additive component. So as long as we have balanced latency between these 3 components, we can develop low latency fabrics. Interestingly enough, the only thing you can really do about the scheduling latency is to increase the bandwidth of the device. So adding ports to the switch will reduce the scheduling latency for the same amount of load into the fabric. So to add a pictorial argument to, or description to those points, we looked at, so if you assume that the average store and forward latency is 3 microseconds, And we're looking at 3 and 5 hop fabrics. With a 3-hop fabric, you very quickly, at about a kilobyte, get to 15 microseconds of latency and about 30 microseconds with a 5-hop fabric. Whereas with a cut-through device at 5 hops, you're at just a microsecond, and that's independent of packet size. So definitely in the zero load case, you can create very low latency fabrics. But then, of course, the question is, what happens with load? So we did some simulations where we looked at peer-to-peer connectivity. We looked at multiple sources talking to a smaller number of uplink ports and in both directions. And what we found is that when you have collisions, that as long as the fabric, it's essentially linear up to about, up to full bandwidth. And most of these different types of scenarios give you essentially the same graphs. So most Ethernet fabrics or LANs really are only about half full. In fact, I would definitely recommend that if you are trying to run a fabric at 70 or 80 or 90% full and it's Ethernet, or really any type of data center switch, you should really add more ports. You should add more bandwidth. So if you look at the kind of the worst case where you're about half full, you realize that about 60% of those packets go through a switch unencumbered and achieve that 200 nanoseconds latency. The other point I'd like to make is that as you have a multi-stage fabric, the benefit of going through the switch without a collision, it simply adds as you go through multiple hops. So when you look at kind of a realistic fabric with realistic load environments, what we see is that you can get tremendously good latencies with these types of switches. Here we've done something where we looked at 16 servers with either 4 or 8 uplinks, assumed about 25 gig of total uplink bandwidth, which is about as much as we would expect to come out of individual servers. And assuming 3 microseconds for the average case, or the typical vendor case, and 150 nanoseconds for FocalPoint, we see that even in the loaded case, we're 1 to 2 microseconds for a 5-hop fabric, whereas a store and forward fabric under the same amount of load is about 10x that, or 20x that for jumbo frames. So you can build very low latency fabrics with Ethernet as long as you have adequate port density and you have 200 nanoseconds or so of latency through the switch. Why is that important? Well, the NICs today have about 10 microseconds, or in some cases much better, but about 10 microseconds application to application latency. And the recommendation for the switching infrastructure is that that should only be 10 to 20% of the overall latency. Because if you go above that, then depending on how the application is spread out across various nodes, it can see different latencies. And if it sees different latencies, then you're exposing switching latency to the application, which is an intractable problem to code against. So this is why we feel that this is the right bar for Ethernet capability that allows us to be able to do any of the types of networks in the data center over an Ethernet infrastructure. The last point I'd like to make is on scaling. And so the way we go out to thousands of nodes is to introduce cross networks into Ethernet. And the idea here is that there's a constant cross-sectional bandwidth from the ports to the servers between a first layer of switches and a second layer of switches. And with that, and with the proper statistical argument on the distribution of the flows, you get non-blocking bandwidth. And this is recursive. You can go to 3 or 4 layers of switching to scale even further. But the one issue is that the number of chips you require is quadratic in the number of layers of switches. So it's extremely important to have a very high port count per switching device. And over here with a 2-tier fat tree, we see that you can get to 288 10 gigabit Ethernet ports with a 24-port basis chip. But if you only have a 20-port basis chip, it's only 200. Or for a 3-tier fat tree, 3, 4, 5, 6 versus 2,000. So that kind of leads us to the last test for whether this technology works, which is what we call the 737 test. And that is something we learned back 3 or 4 years ago, which is that if a routing or switching network costs more than a 737, no one will buy it. So having gone through the motivation of why we built the chip we built, let's now go into the architectural details of the chip. So our project goals was to achieve 24 10 gigabit ports, as I mentioned, and the 200 nanoseconds of latency. But we also wanted to make a pure shared memory fabric, because as you start adding ports, really the most precious commodity on the switch is the memory. And you really need to share that memory across all those ports. And a pure shared memory switch is very good for that. You can get situations where you can have multicast input on the device on all ports, and you have to be able to handle those cases. We also wanted to make the device standards compliant and feature rich, which means QoS and lots of Ethernet features. And we wanted to go after a standard manufacturing process, TSMC 0.13 FSG, with all ordinary CAD flows and flows after GDS. So often as a fabless company, you don't think too much about what happens after GDS, but really we wanted every single flow from when we taped out to when we ship in production to be all standard. And lastly, our project goal was 1 watt per port typical power, so that this would fit in bladed systems and power-sensitive systems, as well as in big systems. In order to create this device, we had to use some secret sauce. So we have 2 architectural enabling circuits, which really allows us to close the architecture in 130 nanometer technology. They are crossbar and our packet storage technology. The crossbar, we call it Nexus. It's really an amazing piece of technology. It takes only 3 nanoseconds to arbitrate for a link and to send the first bit through. It has about a terabit of bandwidth per square millimeter, and that's in 0.13. And it has usage-based power consumption. So one of the issues with networking is, of course, you have to design in all this extra bandwidth to handle corner cases, which almost never happen. But you don't want to consume power for all that extra bandwidth. So the usage-based power consumption was very important for that. In addition, we also have a memory technology, which worst case performance is about 720 megahertz, a little higher than that. And what's so important about that is that in a pure shared memory switch, you have an event rate issue where you could hit any memory location at twice the packet rate. So 24 times 10 gig is 360 million packets per second for Ethernet, which has a minimum packet spacing size of 84 bytes. So you need 720 megahertz memory. If you have 720 megahertz memory, you only need single-ported memory, which makes this device much more manufacturable. In addition, this memory technology is optimized for small block sizes, which allows us to do some pretty aggressive striping architectures, as well as use the memory in all sorts of interesting places, which was really essential to close the architecture. So the memory technology that we developed, it uses a standard TSMC state bit. There's nothing unique about it at that level, but it uses the crossbar types of circuits, bus circuits for the address generation and the read-write environments. And it's also embedded into a set of crossbars, which allows us to create a non-blocking infrastructure. So now I want to show you the architecture of the chip. It's a pure shared memory switch. It's broken up into 5 blocks. There's the RX and TX port logic, which were optimized to be very thin so that we could replicate them 24 times without taking a lot of die area. These unique enabling circuits I just mentioned are really used in the switch element data path. That's where you have all of the bandwidth and memory requirements, but there's not a lot of sort of register level complexity in these circuits. So we could use a custom circuitry, which is really dense and carefully handcrafted. We talk a lot about crossbars, but I should point out that this is not a crossbar-based switch. It's not an input-output buffered crossbar-based switch. Instead, we use crossbars to make a fully provisioned shared memory. So the way it works is a packet comes in. That packet will stream non-blocking through the crossbar, the input crossbar into the memory. So 24 ports, 24 input ports into actually 16 architecturally visible banks of memory. And as that packet comes in, it's broken up into 64-byte segments. Those segments are striped across the memories. So there's no blocking on the crossbar, and the queuing happens centrally where you can apply congestion management policies and really look at what's high priority versus low priority, what ports are using memory in what way, and apply those types of congestion management policies. In addition, it's got a central frame processing pipeline. Really, all of the Ethernet personality is done in one central pipeline. That pipeline is completely deterministic, and it runs at 360 megahertz. So it's doing one header per clock. And it really only takes about 50 nanoseconds from when you first see a packet to when you know all the output destinations, including the multicast destinations. So that's the architecture of the device. Just to go a little more deep into the latency, people say, well, how did you get 200 nanoseconds of latency in Ethernet? And the answer is it's actually pretty hard. But you see that there's about 50 nanoseconds in just the SerDes, and that was after significant optimization. So that's a kind of a fundamental limit with switching technology. There's 50 nanoseconds in the store and forward segment that I mentioned. The frame processing is actually done in the latency shadow of that store and forward segment. And then the crossbars and some additional pointer processing logic takes the rest. So it's actually very challenging to get to that level of latency, but it is essential to making high performance fabrics. So we went through all that effort. Lastly, the other point I want to bring up about how do you really introduce this type of high performance into Ethernet? Well, one thing you have to do is you have to come to the table with all the features that customers expect of Ethernet systems. So a complete feature set. From a bridging perspective, 16K MAC addresses, all of the spanning tree variants. You have to be able to do learning and aging on a per port basis and flood control. Fully provisioned VLAN tables. We can actually do double tagging and create port-based flood groups. And do independent VLAN learning. So you could actually do a spanning tree for each VLAN. For QoS, we have per port and shared memory watermarks, both for PAWS, for lossless-based fabrics, and for packet discard for fabrics which use packet discard as the means of congestion management. In addition, there's 100 queues overall in the switch, 4 queues per output port. And for transmission selection on each queue, you can do strict priority or weighted round robin and do that separately on a per port basis. There's link aggregation capabilities, there are security features. In fact, there's an entire layer 2 classification engine to be able to monitor flows, to discard certain packets, to be able to change the priority, et cetera. And there's even 1,064-bit counters in the device for all the Ethernet compliance. So we had to do that to have a credible device. But then on top of that, of course, we want to differentiate ourselves versus the other people in this space. And what we look to do for differentiation is to really enable high performance computing over Ethernet fabrics. To do that, we made a very flexible link aggregation where we can take up to 12 ports in a link aggregate group. And we actually create class architectures using link aggregation. So one of the things that the InfiniBand marketing people have done is said, well, with spanning tree, you can't create fat trees. That's actually not true. And the way we do it is the line chip actually participates in a multi-chip link aggregate group over the fabric chip, which is unaware of the link aggregation. So let's say that you don't know any addresses and you have to flood to learn addresses in spanning tree. A MAC comes into the first line chip and it's flooded. So it's flooded back down to all the input ports, but it's only flooded into one fabric chip because the fabric chips are all in a link aggregate group. The fabric chips don't know about the link aggregate group, so they flood out to all the other line chips. And now there's a copy of the frame in each of the line chips, and that will flood down to all the network-facing ports. But since this egress line chip thought that the frame came from a link aggregate group, it will not flood back into the fabric. So we've now done flooding through this chassis or through this fat tree system without any loops. So you can run spanning tree on those fabric chips, but it won't turn off any of the links. The other key point is you have to make the hashing symmetric, because for spanning tree to work, you have to traverse the same path in both directions. So if you change MAC B and MAC A, you want the link aggregation to resolve to the same fabric chip. We have that capability as well. We also support a stacking topology in server clustering fabrics. So those are the features. Now, when we finish the project, as a chip guy, I love to put up die photos. I can stare at this die photo for weeks, as can many people back at Fulcrum. But one thing I definitely wanted to point out was where the crossbars are in this chip. So this right here is a 10 gig SerDes from a leading SerDes vendor in the industry. This is our Ethernet port logic I mentioned. So this whole thing is a 10 gigabit Ethernet logic, pretty dense. This right here is a terabit crossbar. So the terabit crossbar has 100 times the bandwidth, but is only 3/4 of the area. And that's really the technology that enabled this level of scale. So where are we? Is this just a paper tiger? Well, actually, no. We taped out the device in Q3 of last year. We got our silicon back December 1st. We had packets running the next day. We shipped our first evaluation platform December 31st. We've since gone through a number of customer engagements. We've had customers announce products. We've even had external people evaluate and publish results on our silicon. And we're now today in production meeting early demand. And you should see systems coming out, end user systems in the market later on this year and next year. We're all very excited to see this happen. Please look carefully in the press. This is an example of some of that early customer validation. This is Force 10 announced a product, the S2410, and Tolly did the marketing behind that. They actually took 24 10 gigabit Ixia testers and fully tried to break our switches as well as they could. And you do a mesh round robin test with that where you send one packet in and you rotate through that round robin. We get no packet drops at any packet size. They were also able to measure about 250 nanoseconds across all packet sizes, and this is while the switch is fully loaded, so not a single packet test, but a fully loaded test. So we're very happy with those results. Now lastly, I just want to talk a little bit about some of the applications that are now possible with this device in the data center. But first, let me just talk about some of what's coming in the ecosystem. So far, we've had a couple of NIC vendors announce results with our switch. Miracom, which is well known for the MirrorNet interconnect, has a 10 gig E mode in their NIC, and they used our switch, and they got 2.4 microseconds end-to-end latency, an absolute record for Ethernet. And in fact, it's just as good as their proprietary solution at 2.4 microseconds. And what we were surprised about is it was almost half of InfiniBand's latency, which is about 4 microseconds in this type of system. Ohio State University did some results with NetEffect, which showed an entire iWarp stack, which is like layer 4 plus processing, all on the NIC, running at under 10 microseconds. And there's a lot of results which are coming. They're not public yet, so I can't talk about them. But stay tuned for those. This picture is a picture of a 288 port switch done with the Kloss architecture. It's a two-stage fat tree architecture. It's done in both copper cable and optics. And since it takes 3 switch hops, it's about 0.6 microseconds of fall-through latency. This type of device takes 36 of our chips and uses no unusual silicon. It doesn't have 5 different types of silicon to implement different types of backplane functions. It's really just this one switch, which is replicated in a Kloss architecture. There's significant industry interest in this. Please stay tuned for more news to come. And one of the things which I find fascinating is it's so cost effective. In some cases, it's almost less expensive than just the cables that are used to connect the switch. But as I said, this is all based on hashing. And so you have to ask the question, for this application to work, how does this application work? So we did some results with hashing, and we were able to show with a pretty reasonable type of typical application about a plus or minus 5% on the hashing asymmetry between the different ports just using layer 2 MAC addresses. And it gets much better once you start using higher layers on top of that as well. With that 5%, or with the 95% distribution like that, you can get about 98% of the bandwidth in these types of fat trees, because a couple of percent of that bandwidth is terminated locally. So what we want to do is say, well, do we have enough memory? I mean, does this system actually work? And so what we found is that even running in this backplane at about 95% utilization, it really only requires a few tens to a few hundreds of packets in the switch at any one time. And so for ordinary Ethernet packet sizes, you can do about, it only takes a small fraction of the memory for the switch to keep up. And that's at 95% bandwidth. These systems also scale to 3-tier fat trees. So for example, you can do a 3456 port non-blocking, or you can do 4608 if you do 2-to-1 oversubscription. And my last slide, I just wanted to show you the available bandwidth in those. We did a simulation of total frame size versus what bandwidth you could achieve before you discarded the first packet in these types of systems. At the 2-tier, we actually got about 98% over the legal Ethernet frame range, and for a 3-tier, about 96%. So very excited about the prospects of data center Ethernet and what low latency can bring to the data center. Thank you.
Time for a couple questions? Sounds like you've got all the answers, Yuri. So thanks a lot. So our next speaker is Masayuki Ito from Renaissance Technology. He has a master's degree from Tokyo University. He's also a visiting fellow at UC Berkeley in 02 and 03. He works on low-power microprocessors, SoC, at the design at the architectural and micro-architectural level. We're going to hear about a new member of the SH family, SH Mobile G1, a dual-mode baseband processor.
Thank you, Chairman. Good afternoon, everybody. I'm Masayuki Ito from Renaissance Technology, Japan. Today, I'd like to talk about the SH Mobile G1, a single-chip application and dual-mode baseband processor. We call this chip G1 for short. G1 was developed by Renaissance Technology in collaboration with NTT DoCoMo. Here is an outline of my presentation. First, I'll talk an overview of cellular phone system. Then I'll explain about SH Mobile G1 architecture. I'll focus on 3 CPU configuration, communication architecture, interrupt control, system control, and power control. I'll show you some measured leakage current data. This slide shows 3G multimedia cellular phone system. The upper figure shows the previous system before G1. A baseband processor together with high power amplifier and RF IC are required for voice communications. Not only an application processor, but multimedia engines are commonly used for high performance applications such as video phones or 3D Java games. G1 replaces these 3 chips by 1 chip. This figure shows a sample of system architecture using G1. This brown box is G1 hardware. G1 has 3 domains, a baseband domain, and an application system domain, and an application real-time domain. Each domain has a CPU and on-chip buses connected to the next domain by bus bridges. Each CPU runs a different OS, so G1 system architecture is a multi-OS on heterogeneous multi-CPU cores. The baseband domain handles both wide CDMA service, high-performance 3G mobile network, and GSM GPRS, available worldwide. Application system domain runs a general purpose OS like Symbian or Linux, handling file system, Java, and device drivers. Various applications such as camera, mail, video phone, and so on are connected through APIs. The real-time domain plays role on video, camera, and audio, handled by powerful multimedia engines integrated in this domain. Here is a list of motivation for one-chip integration. First of all, chipset cost, the biggest factor. And mounting area can be decreased by sharing common peripherals, and performance can be upped by wide data throughput. Dynamic power can be saved by low-load inter-domain signals compared with high-load inter-chip signals through LSI pins. Static power can also be saved by leakage current shutoff by power down, by shutoff powers for unused domain. This is a chip overview. G1 was developed by 90-nanometer low-power process CMOS dual VTH process technology with 8 metal layers. Supply voltages are 1.2 volt for internal core and 1.8, 2.5, 3.3 volt for IOs. 181 million transistors, or 13.5 million gates, are integrated together with 20.2 megabit memory bits in G1. This figure shows a G1 module block diagram. CPU core blocks are colored in blue, and on-chip buses and bus bridges are colored in yellow. Application real-time CPU core block is here, connects to superhighway bus. Superhighway bus is a 16-4-bit split transaction bus, achieving very high performance data transfer. This superhighway bus is connected to another superhighway bus by superhighway to superhighway bridge, or S2S, shown here. And the application system CPU block here is connecting to this superhighway bus. This superhighway bus is connected to HB bus in the baseband domain through AP-BB bridge. This AP-BB bridge connects the application domains and baseband domain. Baseband CPU core block here connects to the HB bus here, and wide CDMA block is connecting to baseband main bus from HB bus, and GSM block here is connecting to APB bus from HB bus. We have a system controller and wake-up controller as common modules, independent of these three domains. They mainly control power downs and wake-ups. Now I explain more detail about these three domains one by one. Application real-time domain. The CPU is SHX2. SHX2 is a Super H architecture CPU used in SH Mobile series CPU. And SHX2 is a two-way superscalar running up to 312 megahertz. This is the most powerful CPU in G1. 32 kilobyte instruction cache and 32 kilobyte data cache are integrated, and 512 kilobyte on-chip RAM is available in this area. This on-chip RAM is mainly used as VRAM to store data for LCD display. Various media IPs are integrated in this domain, connected to this media bus. VPU, or video processing unit, encodes both MPEG-4 and H.264. VIO, a camera interface with image processing engine, handles up to 5-megapixel camera. We have 3D graphic accelerators and JPEG coding unit as well. Application system domain. The CPU here is ARM926EJ, runs on general purpose OS, running up to 208 megahertz. 32 kilobyte instruction cache and 16 kilobyte data cache is integrated in this CPU. Various peripherals are prepared for handling this domain as an application processor. There's sound handling, SD card interface, I2C, flash controller, USB, and some serial modules to communicate with the baseband domain. Baseband domain, the CPU is ARM926, and it runs on real-time OS, running up to 104 megahertz. 16 kilobyte instruction cache and 4 kilobyte data cache with TCM are integrated. TCM is one cycle access RAM for ARM CPU. Both wide CDMA and GSM GPRS block have DSP that accelerate the modem protocol handling. GSM GPRS can totally be powered off where only wide CDMA service is available, and vice versa. Only small logic in this domain is awake for tracing the timing of each radio. And the rest of the logic is powered off to reduce the leakage current and to save the battery life. Communication architecture is one of the most characteristic features in G1. G1 keeps the communication path used in the previous system in order to maximize the use of the huge software assets in the previous system. For example, in the previous system, baseband LSI and application system LSI communicated by these serial modules. In G1, though G1 is one chip LSI, the same serial modules are integrated for the software reuse. Application real-time LSI has a MFI module, multifunctional interface. This MFI module contains a communication RAM and communication registers that can be accessed by application system LSI through memory access interface. Now in G1, both application system domain and RT real-time domain are integrated. MFI still exists. And application system CPU can access this MFI through memory controller. Note that we have another MFI here under the control of application system domain to communicate with the baseband domain. This MFI module contains the communication RAM and boot ROM to share with shared by baseband CPU and application system CPU. Since G1 has bus bridges, so basically every CPU can access any modules in the chip. Application system domain and application real-time domain are very tightly connected, so they share SDRAM and memory map. However, application domains and baseband domain are very loosely connected, so they have different SDRAM and different memory map. Although they have different memory map, APBB bridge supports access window scheme to access the resource in the other memory map. You can set the register to map any region of baseband address in the application address map. Interrupt control. Each CPU has its dedicated int controller. Int controller for application system domain and real-time domain has a cross path to notify interrupts to the other CPU domains as well. MFI module can generate inter-domain interruptions from the CPU, and some external pins can generate interrupts for each CPU. System control. We have a common CISC module here and 3 symmetric interfaces for each CPU. Each CISC interface has a semaphore register, power down register, wake up register, and boot control register. Each CPU can read and write these registers. We have 2 CPGs to control reset and clock for each domain and each modules. Boot control. One master CPU defined by external pin settings boots first and specifies the other CPU's slave addresses. So the slave CPUs are waiting for the master CPU to kick the start bit for them. Various boot modes are prepared for easy software development and software debugging and hardware tests as well. These are the examples of boot modes. You can choose the master CPU and boot address for the master CPU. Power control. Each CPU can read and write CISC registers from each domain, which are reflected into the common CISC module. In order to avoid the conflicts of power control, the CISC module has a semaphore control function. So only one CPU can get the semaphore at one time. So power up, down can be controlled by the only CPU that gets the semaphore at that time. Clock control. Application domains and baseband domain have separate clock pulse generators, which means application part and the baseband part can work independently and asynchronously. Many variations of clock configuration gear changes are supported for the system to choose the appropriate clock combination for dynamic power reduction. However, clock for some IPs like USB or serial modules remains the fixed frequency regardless of the bus frequency or CPU frequency. G1 has 20 hierarchical power domains for partial power off. We have 2 common power domains called C5 and C4. System controller and pad controller belong to this power domain C5. In power domain C4, repeater cells and clock buffers and hardware backup registers exist. There are 8 power domains for application domains and 10 power domains for the baseband domain. These arrows show that the power domains have relation. And a power domain in the upper part, shown by the head of an arrow, should be powered up for the power domain in the bottom to be powered on. This is a chip floor plan, and the right figure shows the corresponding power domains. The name of the power domains are shown here. You can see that C5 domain and C4 domain, they are always powered on domain, are very tiny regions where only small amount of logic exists. Here are implementation results of power domains related design. The number of power domains is 20, and the number of islands for C4 is 19. Recall that repeaters and clock buffers and backup registers belong to this power domain C4. So C4 domain is scattered into 19 islands inside G1. The number of repeaters and clock buffers and backup registers are shown here, and number of micro-IOs are 20,000. Micro-IOs are isolation cells that are inserted between power domains in order to avoid the signals from powered off domain coming into power on domains. Total area of power switch is some 4.2 square millimeters. Now, let me show you some measured leakage current in some usage scenes. Powered on domains are colored in red, and powered off domains are in black. The first scene is video telephony. All the power domains are on, and the measured leakage current at the room temperature with 1.2 volt is 849 microampere. The next thing is telephony at wide CDMA area. Now, application real-time domain is powered off, shown here. And the measured leakage current is now down to 407 microampere, about half as the first scene. The third scene is waiting for calling. Now the baseband controller part is on, but the wide CDMA part is off, except for intermittent operation. Now the measured leakage current is down to 299 microampere. The final scene is power off case. All the power domains are off, except for C5. All the clocks are stopped, except for slow 32 kilohertz real-time clock. Now the measured leakage current is only 7 microampere. Here's a summary. We have developed SH Mobile G1, an application and dual baseband single chip processor for 3G multimedia cellular phone system, and some of key features of its architecture have been presented. We have shown that one-chip integration contributes not only to dynamic, but also to leakage current reduction by careful partial power off control scheme. Thank you for your attention.
Some questions from the audience? Here we are.
Hi, I'm Sorin Sesmas from Mobiligen. I have a question regarding the video portion. What type of resolution is the H.264 encoder supports? Is it QVGA, VGA?
Sorry, I can barely hear you.
So regarding H.264 encoder, what resolution do you support?
I'm sorry, I haven't the detailed data right now.
Do you have also some active power numbers? What is the power consumption during active operation of the chip?
Power consumption?
Active power.
Peak power.
Peak power for the chip. It's about 300 milliampere in the worst case in the total G1 chip.
Okay, thank you.
So Masayuki, I have a couple of questions. What is the status of the chip? Is it in production?
Yes, it's in production, and yeah, the first product using G1 will appear soon in Japan.
Okay.
Yeah, next month.
Next month. Okay. Definitely in production. A couple of little announcements. The slides from the two keynote speeches for yesterday and today are now on the Hot Chips website, and attendees can get those slides. We have one more speaker before break, and we're going to have ice cream at the break today, so just something to look forward to. Our next speaker is Balakrishnan Sundararaman from Agere Systems. He's a distinguished member of the technical staff, has an MS in electrical engineering from the University of Hawaii. He has worked in networking at Force Systems, Marconi, Laurel Networks for 8 years before joining Agere in 2004. He leads the traffic management team in the network processor design group, and he's going to tell us about the APP300 access network processor.
Hi, I'm going to be talking about the APP300 access network processor that was designed at Agere Systems. The APP300 was designed for the access network. This slide is shown a picture of the network topology. On the left is the backbone of the network, the multi-service edge. This is a high-speed optical network, which is pretty stable. The middle is the access systems, which is where a lot of the ongoing deployment is. It's an ATM network right now, but service providers are rolling out new services here. This consists of your wireless base stations or node Bs, which aggregate your cell phone calls, and then the digital subscriber line access module and the multi-service access node, which aggregate your home and business networks. And on the right is the customer premises itself, and this is where there's going to be a lot of activity in the future. This consists of your cell phones and also your home network and business network, where a lot of intelligence is going to be added into the networks here. The APP300 can be used in all the access systems deployment as well as in your home and business network. Our approach to designing this network processor had 2 steps. The first was to have a highly pipelined, wide-speed data path that is programmable, and the programmability is important. And the second is to have an embedded processor that can be used for all your control processing. Some of the alternative approaches that have been taken, first one is to have an array of microprocessors with some program and data storage, and every packet that comes in is actually processed by one of these microprocessor cores. This works well when you have lower bandwidth, or you don't have to do too much functionality, but starts falling behind for higher speeds. Also, another problem here is that since every packet is handled by software, anytime you do a software tweak, you can actually get a difference in performance. Another way to do this would be to design a custom ASIC for this. Obviously, it comes with high development cost and long time to market. But I think another significant disadvantage is that this is an emerging market. As requirements change, you don't have the flexibility. So our approach tries to kind of combine the best of both these approaches, try to have a full wide-speed data path, but at the same time add programmability to it. So this slide shows the main processing steps as a packet goes through our chip. This talks about the data path mainly. As packets come in, they go through some physical layer translation, and then the packets can be reassembled if required. I'll be going through each of these steps in more detail. The packet is recognized and classified, and then the packet is queued and sent out using a traffic shaping script, and packet can be modified on its way out, segmented, and the packet itself is sent out. At the end of classification, if you want, you can collect statistics and apply policing treatments on this packet. And there is also a way to send traffic to and from the host processor. This slide shows a block diagram of our chip. I'll be going back to this slide a few times as I walk through all the different blocks. I'll first talk about all the interfaces of the chip. Then I'll be talking about the classifier, which is the top left here, and then about the traffic manager, which is on the right, and finally about the control processor, which is an ARM9 core. The interfaces on the APP300. Data can come in through a data path port or a coprocessor port. The data path port is 32 bits wide, but can be set up as 4 8-bit ports or 2 16-bit ports or any combination thereof. And it supports a wide variety of protocols, Utopia 2, Utopia 3, POS2, and SPI3. And there are also built-in Ethernet MACs on this chip, so it supports all the Ethernet protocols. There are 3 external memory interfaces. I'll talk about these in the next slide. There's also an integrated ARM926 processor that I mentioned, which interfaces through a 16-bit PowerQuick host interface and supports many peripherals, I2C, SPI, UART. And there is also a 1000 Ethernet MAC on this chip dedicated to communicate with the ARM. All control and data structures that are needed for the operation of this chip are in one of 3 external memories, and all these memories are DDR2 SDRAMs, so there are no expensive SRAMs or CAMs that you need to interface to. And this is a pretty significant shift for network processors. A previous generation architecture, for example, used 6 FCRAMs and 5 DDR SRAMs, so this is down from there. The first memory is the control memory, which is a 16-bit DDR2 SDRAM, which is used to store classification and traffic management control structures. The second one is the data memory, which can be 16 or 32 bits wide and is used to store PDU data. And the third memory is used for ARM program and data. All the memories have optional ECC protection. There's more than 800 kilobytes of internal memory on this chip, and this memory is shared between 8 clients. The memory itself is divided into 32 chunks, varying in size between 8 kilobytes and 256 kilobytes. And there is a configurable crossbar that allows you to assign different amount of memory to different clients. This is an important feature because depending on the application where this chip is used, and there can be quite a few different ones, each client might need a different amount of memory, so it gives you the flexibility to do that sort of assignment. The first block that I'll be talking about is the classifier and policing engine, which performs reassembly, packet recognition, classification, and then applies policing treatments and collects statistics. As packets come in, they go through an input interface, they undergo classification, and then the policing and statistics operations before the packet is passed on to the traffic manager. In the classifier, you can do programmable classification up to layer 7 using the functional programming language, or FPL as we call it. When a packet comes in, you want to look at some bits in the packet and decide what you want to do with this packet. With FPL, this is under software control. So anytime you want to implement a new protocol, you can write the description in FPL and set up a table in memory and use that to do your classification. Obviously, this reduces your development time and time to market because you can easily support new protocols. You can do ATM reassembly on this chip, so you don't need an external SAR. Classification is done using a tree-like structure that's stored in external DRAM. So this table can scale to millions of entries, and you don't need a CAM, so there's no, performance is not dependent on the table size. There is also an on-chip tree cache that can be used to speed up processing. support Utopia and pass interfaces, and there is a built-in receive MAC, so you can support Ethernet traffic. The policing engine in this block is very programmable. The policing engine is one of 4 what we call compute engine processors that are there on this chip. A compute engine processor is a simple microprocessor for which you can write a script in a C-like language. So when a packet comes in, the script gets executed, and the result of your script is the policing treatment that gets applied to the packet. There is also OAM support in the policing engine. Shown in this slide is a block diagram of the classifier. The heart of the classifier is the pattern processing engine, which is a very parallel engine that works on multiple threads or contexts. It uses a tree structure stored in external DDR memory, and there's a tree cache to speed up processing, and it does classification using that. When packets come in, they either come through the input framer, if it's parsed or Utopia traffic, or through a receive MAC if it's Ethernet traffic. The packet is parsed and reassembled if reassembly is required. Once we have an entire packet on chip, the packet is read out of memory, and the pattern processing engine performs classification on the packet. And at the end of that, you can collect statistics and apply policing treatments using the functional bus interface. And then the packet itself is passed on to the traffic manager along with the results of the classification. Results of classification is a destination ID and some flags which are used by the traffic manager. The next major block is the traffic manager that does queuing, traffic shaping, packet modification, and segmentation. The traffic manager receives the packet from the classifier along with the classification results, goes through the traffic managing steps, and then sends the packet out on the output interface. The traffic manager supports 2K queues and has 6 levels of scheduling hierarchy. I'll talk in detail about the scheduling hierarchy in another slide. It can do programmable shaping, implement programmable discard policies, and has support for quality of service and class of service queues. There is support for multicast, and it can generate all the required checksums and CRCs, and has Ethernet support through transmit MAC. The traffic manager supports a large number of connections, and it's very programmable to support different applications. It has 3 compute engine processors in it. The first one can be used to do traffic management, or what's really buffer admittance control. The second one can be used to do traffic shaping, and the third one is used to do packet editing. Shown here is a block diagram of the traffic manager. Packets are received from the classifier through the input interface, and the result of the classification is the destination ID. Based on the destination ID, the traffic manager figures out on which queue we want to put this packet. Once it figures out which queue this packet is supposed to go into, it executes the traffic management script. So you can implement any buffer admittance algorithm that you want here. You can do weighted read if you want, or if you have ATM traffic and you want to do early packet discard or partial packet discard, you just need to set up your scripts accordingly. Once we make a decision on whether to accept a packet or drop a packet, let's say we assume that we want to accept this packet. The packet is put at the tail of the queue. Independently, there is a scheduling process where the traffic shaping engine comes into the picture, which picks a queue that needs to be transmitted next. We read the packet that's at the head of this queue, and then we send it over to the stream editor, which can edit the packets before it sends it out on the output interface. Scheduling hierarchy. We talked about how the data path port in this chip can be set up as 4 8-bit ports, and there is also a coprocessor port to get traffic in and out. There is also a management port that's used to send traffic to the host processor. So there's a total of 6 output ports that the traffic manager supports. There are 256 port managers that are supported in this chip. A port manager is the level at which you can specify a rate. You can say that I need a port manager which is 100 megabit per second, and it would be guaranteed to get that rate. Logical ports are a way of carving up port manager bandwidth. You can map 1 or more logical ports to a port manager. You can have up to 4 schedulers per logical port. We support a total of 1K schedulers on this chip. There are three types of schedulers: static, dynamic, and FIFO schedulers. Static schedulers are typically used for constant bitrate traffic, dynamic scheduler for variable bitrate traffic, and FIFO scheduler for unspecified bitrate or low priority traffic. I'll talk in detail about how all these three schedulers are actually implemented. The dynamic and FIFO schedulers are under the control of your traffic shaper script, so that gives you a lot of programmability. And finally, there are two levels of hierarchy within queues. Queues can be mapped into schedulers. There are two levels of hierarchy within queues. There's a quality of service queue and a class of service queue, and you can map 16 class of service queues into one quality of service queue. So let's look in detail about how each of the scheduler types work. First is the static scheduler. This scheduler is implemented as a table in memory, and software programs this table. So when it's time for this scheduler to transmit, the queue that is at the location of its current pointer is read out, and then the scheduler moves on to the next slot in its table. The second type of scheduler is the dynamic scheduler. It's again implemented as a table in memory, but this table is not programmed by software, but is entirely under hardware control. Similar to static schedulers, when it's done for this scheduler to go, you read the queue at the current pointer, but you can actually reinsert this queue in any location in this table, and that is under the traffic shaper script control. So this gives you, suppose you wanted to implement an algorithm where you have a queue that sends some number of packets at a peak rate, and then you want to back off to a sustained rate, you can write a script to do that. And hardware handles the case when there are multiple queues in a time slot. The third type of scheduler is the FIFO scheduler. This is used for best effort traffic. It has lower priority than the static and dynamic schedulers. The FIFO scheduler is implemented as 4 lists of queues. There's an active list and 3 pending lists. We always schedule from the head of the active list. And when the active list is out of queues, the first pending list becomes the active list, and we rotate everything around. When a queue comes out, it can be scheduled in one of 5 places. It can be either put back in the active list, or it can be sent to one of the pending lists, or it can be sent to a penalty box where the queue has to wait for a while before it can schedule again. So this is all under traffic shaping script control. Suppose you have a queue that you want it to be scheduled fast. You can keep reinserting it into the active queue, into the active list. Or you can send it to one of the pending lists if you want to slow it down, or to a penalty box if you want to slow it down for a while. The last block that I'll be talking about is the host processor and the host processor subsystem. This can be used to send traffic to and from the data path. The host processor on the APP300 is an ARM 9 core and has an external DDR SDRAM, and it can also boot from a flash. This is a block diagram of the ARM subsystem. It has an ARM 926 processor core. There is a host packet block that can be used to send traffic to and from the data path. There's a dedicated 10100 Ethernet MAC that can be used to communicate with the ARM. There is a memory controller for the DDR2 memory that interfaces to the ARM, and there is also a host bus interface for the PowerQuick host bus. All of these communicate with the ARM processor using an AHB bus matrix. It supports various peripherals, UART, I2C, SPI, et cetera, which are on an APB bus, and communicate to the AHB bus matrix through an AHB to APB bridge. The ARM 9 core has a low silicon and royalty cost and has more than adequate performance. It supports DDR2, Ethernet, and flash interfaces and a variety of peripherals, and can send packets to and from the data path. There is also a modem configuration interface. It's a programmable interface that can be used to initialize modem chips without using any additional glue logic. So this and the fact that we have a processor on chip brings down the BOM cost of any board that you want to build, because you don't have to put down an external processor. Because if it so requires that your application needs a lot of processing power, then it can work with an external processor. From an IC perspective, This chip is about 150 square millimeters in a 6-layer metal 0.13 micron process. There are 9 million logic gates on chip, 12.9 megabits of memory. The core clock runs at 166 megahertz. The ARM and DDR run at 200 megahertz. There's support for a variety of interfaces. There are 2 PLLs on chip which are used to derive all the clocks in a programmable fashion. It uses a 744-pin package in 1.27 millimeter pitch. This is a picture of the IC. Right in the middle is where our 800 kilobytes of internal memory is. These are the major blocks, all of which actually end up talking to this memory block here. Depending on the frequency at which you run this part and whether you use a 16-bit data memory or a 32-bit data memory, its advertised performance is between 300 megabits per second and 2.25 gigabits per second. But in fact, it can sustain a bandwidth of 3.3 gigabits per second, and it has a classification bandwidth of 192 bits per packet when running 64-byte packets. One of the real-world applications that we tried to set up in the lab was to have 64 modems running full line rate ADSL2, and we sent a real-world traffic mix into it, and we can get 100% packet through the system without any packet loss. We did some measurements on the amount of headroom we have, and we actually found that you could go up to 72-port ADSL2 if you want. So here is an APP300-based DSLAM solution that we built at Agere. On the left are 4 modem chips. Each of them support 12 ADSL2 modems. They interface to the APP300 through 2 Utopia 2 buses. All the traffic from and to the modems are aggregated in the APP300 and sent into the service provider network through gigabit Ethernet and fast Ethernet lines. So in summary, I want to sum up the features that make the APP300 a good fit for the access market. First, interface flexibility. It supports a wide variety of interfaces. It can connect up to a lot of physical layer chips. Second, powerful processing. It's got excellent classification and traffic management algorithms. It has a hierarchical scheduler, 6 levels of hierarchy, and it can do wire speed, and it has a wire speed deterministic performance. It supports a wide variety of protocols, and it's very programmable, so you can build in support for newer protocols if you want. Third, scalability. It covers the entire application range between 600 megabits per second and 2 gigabits per second. Fourth is low BOM cost. We have a built-in processor in this chip, so that obviously brings down your system cost. It uses only low-speed DDR SDRAMs, and also has a very PCB-friendly pinout, so it minimizes the number of board layers. The last is powerful and efficient programming model. FPL is a hardware-optimized classification and pattern matching language. And the compute engine processors that are on this chip, you can code powerful algorithms using very concise scripts. So all this brings down the system cost dramatically.
John?
Yeah, so a couple questions. So when did you guys start the project, and what's the current status?
I'm sorry?
When did you start the project, and what's the current status?
This chip has been shipping for a couple of months. It started early 2004, or late 2003, early 2004. We did first customer samples fall of last year, and been shipping production samples for the last 3 months.
Okay, so now there's a sort of more general question, which actually applies to a lot of presentations at Hot Chips, but I'm asking it for you. I'll probably ask it for some other people. Is that when your presentation comes here, we hear what the chip does, which is good, because we always like information and not marketing, right? I'm always interested in what alternatives were considered. What did you argue about? Did you start with more aggressive requirements and have to back off? What was hard, right? You know, what were the biggest arguments in the design team about trying to jam things in? Like, when did you decide you could get away with just DDR DRAM? So can you go at some of that to give us some insight about how you decided to do what you did, not just how many bits are in there?
I think the fundamental requirements that were presented to us was the BOM cost. They came up with a dollar figure on how much a board can cost. So we had to go back and find out, for example, that more or less decided the size of die that we can get and what sort of package that we can put this chip in. And I think DDR to SDRAMs kind of, from that BOM cost number, it kind of fell in place because, I mean, FC RAMs or CAMs were just out of question there. So once we knew that, we started looking at everything that we have to do, the amount of bandwidth that we have to support, and the kind of pinout that we have to have, and which is, I think, where we did a lot of work, which was trying to take everything that was needed and saying, OK, which memories can be shared in which interface. In fact, when we built this, we built it quite programmable, so we can have different clients going to different memories, different external memories. And then we did some measurements on what the bandwidth requirements are and how they line up, and that's where we ended up with this architecture.
Excellent. Thank you very much.